Okay, so magnetic fields, first homework on force and wires. So if we look at this one, the cross on that circle there is showing that the current is going into the page. So we use the right hand rule to determine, the right hand corkscrew rule that is, to determine the direction of that magnetic field. So the current's going into the page. So as you can see, my fingers, which show the direction of the magnetic field, are going in a clockwise direction. So the field is in a clockwise direction. We then use the same principle for the solenoid. So the current is going up on that side of the solenoid. So current is going up. The field is coming out and around. So there we are. We get a magnetic field looking a bit like that. Right. So then we have a question. We've got wire, 250 milliamps, 90 degrees to the magnetic field. Flux density, 120 millitesla. It's 0.1 meters long. Calculate the force. So it's a simple case of F equals BIL sine theta. Substitute it all in. You get 3 millitesla. This next question, same principle, but we've got an angle of 30 and some different numbers. So we can't ignore the sine 30 this time. So 40 times 10 to minus 3 times 1.5 times 0.2 gives us times sine 30 gives us 6 millitesla. So next question says calculate the current in the wire needed to give the force of 8 millinewtons. So taking the information from the previous page, force is 8 times 10 to minus 3. B is 40 times 10 to minus 3. Length is 0.2. Sine 30. Rearranging for I gives us 2 amps. Right, this question caused a bit of confusion. So it's essentially a moments question with a bit of magnetic field thrown in. So first off, we get the weight of the paper. So there's our paper. We do the weight, the mass times gravity or gravitational field strength. So 0.75 times 10 to minus 3 because it's got to be in kilograms times 9.81 gives us 7.36 times 10 to minus 3. So that's the weight of the paper acting down there. So we just realised I made a mistake there. So to calculate the magnetic field strength or the magnetic flux density, we use F equals BIL sine theta. So our force, we're going to have a magnetic force on that end of the wire that's going down, and that has to be the same weight or same as the weight to balance the wire like that. So 7.36 sine 10 to minus 3 equals B times 2.5, the current, times 5 times 10 to minus 2, that's the length because that's how much wire is in that field, times sine 90 because they're perpendicular. Rearranging for B gives you 59 millitesla. Okay, right, so the next question says, show on the diagram the direction of the magnetic field. Well, this is a bit of a mess right now, so I'll tell you what, I'm going to redraw it over there. So there is B, there's A, the current is going in that direction, the force has to be going downwards, okay, so that we get a moment going in that direction, sort of clockwise. If that's an anti-clockwise moment, that's a clockwise moment, and those two will be balanced. They're equal distance away, so the forces have got to be the same. So again, we know the field's got to go from A to B or from B to A. So the current is going across, the force is going downwards. So using our left-hand rule, force is going down, current is going across. So twisting my arm around, we can see that the field has got to go from B to A. Okay, so let's just quickly correct that. So he's going from B to A using left-hand rule. Okay, right. Next question then. So it says show that the current of 12 milliamps flows through flowing through that wire will produce a field strength of 240 microtesla 1 centimeter away. So this is the equation we want to use. This gives us the field strength around a single wire. So mu naught I over 2 pi A, where A is the distance, the perpendicular distance from the wire. So if we've got wire BC 1 centimeter away, we're working out the field strength at that point there. So we do 4 pi times 10 to minus 7 times 12, the current, over 2 pi times the distance, 1 times 10 to minus 2, gives you 2.4 times 10 to minus 4 Tesla, which is 240 microtesla. It says what is the direction of the force on the wire DE, and how did you determine this? Right, so first thing we have to do, if we want the force on that wire, we need to know on the direction of the force on that wire, we need to know the direction of the field produced by that wire. So this wire is producing a magnetic field, this wire is in the magnetic field of that wire. So again, using the right hand rule, the current goes positive to negative, so the current is going in that direction there. So using my right hand rule, it's coming around the wire like that, so it's coming out of the page on this side of the wire, and it's going into the page on that side of the wire. Okay, so just to demonstrate that again, the current's going in that direction, the magnetic field is my fingers wrapping around. I'm trying to wrap it around, but I'm about to break my wrist. So it comes out that side of the page and into that side. Okay, so out there, into there. So now that we know the direction of the field, so the field is going into the page where DE is. Okay, so we can now use the Fleming's left-hand rule. So now the current is going to be in that direction. So field is into the page, current is in that direction going from E to D. So my first finger is pointing into the page, current is going right to left. So the force, my thumb, which you can't see because my arm's in the way, is pointing in this direction. Okay, so it's downwards basically. So downwards force. Okay, and we use a combination of right hand corkscrew rule and Fleming's left hand rule. Okay, right. So it then says estimate the force on DE due to BC. Well, the field strength at BC, field strength caused by BC at the position of DE is 240 microtesla. Okay, so B is 240 microtesla. The current in the wire is 12, and the length of the wire is 5 times 10 to minus 2. Again, that's in the question there. There's the length of the wire. So that's going to be the length of the magnetic field. The current is 12 because it's one wire. So if the current in that bit is 12, the current in that bit is 12. And the field strength, as we've worked out already, is 240 microtesla. So we multiply them all together, and we get 1.44 times 10 to minus 4 newtons. It says, why is it an approximation? Well, whenever we use this formula, really the wire should be very, very long, if not an infinite length. So it's only an approximation because that wire is only, 5 centimeters long, so it's not very long. So what happens is the other bits of the wire start interfering with the magnetic field. It's not long enough, so you don't get quite that magnetic field strength. So it then says about the suitability of the balance. Well, the force was 1.44 times 10 to minus 4 newtons. That's 1.5 times 10 to minus 5 kilograms, which is 0.015 grams. So really, we want a balance that's got at least 0.00, a resolution of 0.001 grams, because 0.01 just isn't enough really. Okay, right. Then we got this solenoid question. So this is our equation: B equals mu naught n lowercase n I. Lowercase n in this equation is the number of turns per meter. So we have to do the total number of turns, 400, divided by the length, 20 centimeters. That gives us 2,000 turns per meter. So we can now put that into the equation. 4 pi times 10 to the minus 7 times 2,000 times 2.5 gives us 6.28 times 10 to the minus 3. And then last bit of this homework. What happens when we put iron in? Well, in that equation, B equals mu naught Ni. Again, that's really only true of a vacuum. The equation should really say mu naught mu RNI. So that's called the relative permeability, and for iron it's about 100, so it makes the field strength 100 times greater. For aluminium it's like 1.000000025 or something like that. So the increase in magnetic field is negligible, so basically it has no effect on the field strength, whereas with iron it makes it 100 times stronger. And that is all.